Good morning, everyone. Welcome to the gold medal address. So before we start, I'd like to give you a kind reminder. Please turn off your cell phone. You don't want it ring during the talk. So I have my little note here. Yeah, so I'm Grace E. from the University of Western Ontario. So can you hear me well? Okay. Okay, that's good. So it's my honor and privilege to introduce our esteemed speaker, Dr. Charmaine B from the University of Waterloo. Definitely, I know Charmaine does not really need any introduction, but I still want to take this opportunity to give a very quick overview. So Charmaine got her bachelor degree from the University of Saskatchewan in 1980. And she completed her graduate programs at the University of Waterloo and got her PhD degree in 1988. She has a very phenomenal career. After she finished her PhD degree, she joined the University of Calgary for a year, and then she moved to Simon Fraser University, where she became the founding chair of the Department of Statistics and Actual Science. And she also served as the associate director of the Institute for Health Research and Education, and as associate dean for the Faculty of Health Sciences. From 2006 to 2011, she held the Burnaby Mountain Chair, and in 2011, she joined University of Western Ontario, taking the role of Dean of the Faculty of Science. And in 2017, she returned to the University of Waterloo, continued to serve as a professor and vice president, research and international. So definitely Charmaine has a very excellent career path, and she was recognized with numerous awards. So just name a few. She received the CRM SSC prize in 2003. She is a fellow of ASC, IMS, and AAAS. And she is also recognized as one of the most powerful women in Canada. So I guess you might And just recently, I got to know she received a prestigious Order of Academic Palms. Congratulations, Charmaine. So she's a leading figure in our field, making significant contributions in various aspects. So basically, we can group them into leadership and services and statistical research contributions. She has led our fields in various presidential positions. For example, she serves as a and of course, her research includes supervision and phenomenal research contributions. And she has various service roles, including being president or vice president for prestigious organizations such as SSC, NSERC, and the International Biometrics Societies. And she has numerous editorial roles with many prominent journals, including Environmetrics, Statistics in Biosciences, Statistics in Medicine, and Biometrics. So this is a long list of editorship. So Charmaine has developed a diverse and influential research program addressing practical problems in both biostatistics and ecology. So her work spans many areas, including disease mapping, longitudinal studies, clinical trial design, spatial temporal analysis, water quality monitoring, forest ecology, and fire management. Notably, her multidisciplinary research has been very instrumental in connecting statistical scientists, students, industry, and government agencies. And notably, her contribution to wildland fire science and management are exemplary. Her research has significantly advances wildland fire science, influencing policy and practice in Canada. And in addition to that, she has made substantial contributions through her mentorship, supervising numerous postdoc fellows, PhD, and master students. So her dedication to fostering an interdisciplinary learning environment and promoting collaborations has been cornerstone of her career, and focusing on developing new and innovative methodologies for real-world solutions. So without further ado, please welcome Dr. Charmaine B to deliver her speech.
How is it? Can you hear me well? Yeah. Okay, that's. It's on. Just 1 second, maybe 2 or 3. All right. So I have to say that I'm truly honored to be here today to give this talk. And Grace, what an amazing introduction. Thank you so much. So this is going to be a different talk, and I hope that you enjoy it because it's focusing on the words collaborative in the citation that Grace has just read. That has been, I would say, a fundamental aspect of how I approach the work that I do, and I know that it is also part and parcel of what many of you do as well. And it was, I would say, driven by the environment in which I was trained as a PhD student, and the fact that my supervisor was closely entwined with work with industry, and that is what drove his interest in things like reliability analysis, etc. So that foundation, I think, was really important. And I would say that this is through and through the University of Waterloo. You might know that Mary Thompson as well has done a lot of work, and you know of all of her work in statistics and survey sampling, but you may not know of her work related to tobacco control. And for that, she got a Governor General's Award. So the whole idea about collaboration and collaborative work and how important that was came from foundations that not just arose at the University of Waterloo, but also arose through Simon Fraser University, where that was really important for us there as well. So you are right. I will say you were right. I'm going to stand at the side here. You know, so I've put up there collaborative, what I understand by the words collaborative. You know, joint efforts of individuals, and they all have a common goal, and that common goal is not necessarily true in some of the things that we call collaborative research as a society. So I'll push on that agenda through the talk. Applied statistical work is often meant to be collaborative, using interdisciplinary, using knowledge and methods. And you know, the physicists are really good at this with regards climate science. That's so kind of you, thank you so much. And climate models. They work really hard at trying to understand ocean currents, etc., in order to develop our climate models. So they're really good at this, and we're also trying to be the same. I know the biostatisticians have been at this for some time, and the statistical geneticists, for example. In the fields that I worked in, they weren't necessarily part and parcel of how we collaborated with our forest scientists. So when I started this work, because of a request from the Ministry of Forests, actually, you know, there was a lot of concern by some of the key fire scientists that we don't really understand their point of view. So there are two statements there that I heard a lot about: individuals wanting data and wanting to look at data and create student theses from data, but not really interested in helping to solve the key problems that were facing the fire scientists. When in the training at SFU, I have to say again that this was really important to us. Farouk is here in the audience, and I promised to mention him that when he first started to work with me, raise your hand, Farouk. I don't know where you are. There you are, yes. I sent him to sit in the hospitals. I think it was something like a day or 2 days a week, because we were trying to solve a problem with some clinical scientists, and I didn't have time to go. So I sent him to sit there. We got a desk for him 2 days a week, and he tells me that he didn't feel badly about that, but I can tell you, when I remember that he wasn't terrifically happy about having to go sit in the hospitals. And when we started the work on forest fire science, where is Cindy? So Cindy, there's Cindy. So just couldn't understand the data. Really, it didn't make any sense, you know, the trees, the soil samples, etc. Cindy came because she wanted to do mathematical work. She was a keen mind on statistical methods. But I couldn't understand what was going on. And again, I think I was chair of the department at the time, or chair of the stats group. It was really difficult to leave. I sent her up north, and to go up north, you have to do training. Sometimes you have to do weapons training. There's a whole bunch of training that you have to do in order to spend some time up north. I have some pictures of Cindy where she was terrifically unhappy, having to go up north and work with the forest fire scientists, but she came back with a really clear understanding of what we didn't know about the data, and that helped a lot in terms of the collaborations. It also helped Cindy take a fairly serious leadership role with the analysis and the data, because after spending 3 weeks up north with the forest scientists, she became much more closely involved in understanding what was going on. So that's part of the way that I have worked with regards training students, and it's also part of the way of what I think is really important. So, and it doesn't work for everybody. So this is the other essence of the slide. So what a lot of us do here, I would say, is vertical learning, and we need that vertical learning. So we need to really go into depth in understanding a particular problem and analysis in order to make good statistical methods for the world around us. But in order to solve complex problems, we need both vertical learning and horizontal learning. Horizontal learning means that we need to understand the discipline that we're working in, the nuances of it, that's the only way we're going to be able to tell if assumptions are right. So if you think about, vertical learning is here, this is what you're working in, the space you're working in, and you draw a normal curve over that. Most of us tend to go just a little bit outside that in order to understand the nuances. But in order to solve big problems, you have to go to the full scope of the normal curve. You have to really understand all the edges in order to make a difference. I will also say that I've been told that pretty much 2/3 of the audience is here to wait for the end of my talk because there are some great prizes to be delivered. And so I may skip some of the pieces here because I don't want to skip what was really important and passionate to me. So I want to go over some of these, but some other pieces that might be more interesting to some of you in here, I might go a little bit faster on because we've got some young people who want to know where they stand with regards to awards. So I've been asked if I can move it along, so I'll be doing that. Maybe this is one place where I will move it along. Some of you will know that I have little pieces of me that tie into, is there anybody here who's indigenous? And of course mine is from Carib, which is the Caribbean roots, Caribbean indigeneity. Love to see all the focus on indigenous roots, and they have a model for collaboration that they would like individuals who are collaborating with them from non-indigenous cultures to participate with. And I can tell you this model of collaboration really fits the scheme of what I think we need to do when we're working with key big problems. So I'm going to give you 2 case studies, though I may run through one a little bit quicker than another. So this is wastewater surveillance, and it's with a physician by the name of Doug Manuel. It's with an engineer by the name of Rob Delatola, who does wastewater science, and a brilliant statistician by the name of Joan Hu from SFU, and a student who's also quite brilliant by the name of Ken Peng. So you may know that the infection SARS-CoV RNA is excreted into the sewer system, and there are various PCR techniques for detection, and it seemed to be a very effective biological marker. Initially, we did COVID testing, and then when Omicron hit, impossible, too many people, and so that all stopped. But there was still an interest in trying to understand what waves were coming along. And although wastewater testing had been done for some time, that's when it actually became very, very important as a monitoring and surveillance technique. It's also across, that there were dashboards that were providing data related to this, and every wastewater surveillance site uploaded to the dashboard because everybody was interested in understanding it in terms of a global context. So there were 72 countries involved, 289 universities, including University of Waterloo, and Rob Delatola is at the University of Ottawa, and a lot of sites involved within cities. And of course, wastewater monitoring is also used to monitor not just COVID, but a whole variety of infectious diseases. So they were seen, and sorry about this, probably we need our lights dimmed here, but they were seen to capture the trends of hospitalizations, and so thought to be perhaps a good alarm system for when we're expecting a wave of hospitalizations to come forward. And the other thing that's important here is that the correlations over different periods, over different variants, were seen to be different. So it's the lag period between when the wastewater signal spikes and hospitalization spikes is not the same across all the different waves of COVID. So before I go here, I will say that there are things called distributed lag models, Distributed lag models help us explore delayed effects. You know, how far, normal time series model says, you know, how far in the past does a particular covariate or influence a response? And so you can fit those using truncated lag. So you can decide, okay, it's going to be 6 times steps in the past, and then estimate goodness of fit, and then see whether 6 is enough, or 7 or 8, etc., and use that as a mechanism to define the tidal steps. I think I saw Rob in the audience here, so I know that I've read, where's Rob? There he is. Yes, let me see if I remember. There was some work that Rob Tipcherani did on order-constrained lasso. And the order-constrained lasso shrinked the delayed effects to approach 0 for longer time periods. So that is another technique that you can use in order to understand how far in the past. There are also functional forms that you can use, etc. So the questions here relate to that. How far in the past do we need? Can we predict hospitalizations? And this was for COVID, but then now it's for a whole variety of other diseases. And what factors affect the results, and how can we formulate the relationships, etc. So this can be explained rather simply, and it was a creation of the really bright people who were on the team. And I've already named them. So this is a Markov modulated model. And I think part of the, as I look up there, I see some bits are not right. So W are the fixed covariates. So they are the other covariates in the model, and they are affecting now. So they are present today, and they're affecting the response today. And then X, the history of X, is another covariate. So X could be the wastewater signal, and Y could be the hospitalizations, but this is a generic model. So the wastewater signals affect the response, and they affect the response over some period that you're trying to determine. And that period may change from one time step, like one kind of variant of the disease, to the other. So the way, what this model says is that you've got an underlying hidden Markov model. So that Z variable takes values 0 or 1. And it starts off with 1. Yes, today's wastewater signal affects the response. And then it moves through a 2-step chain. So what's the probability that that Z variable, so now we're going backwards in time. What's the probability that that Z variable is also 1 at the previous time step? So that 2-step Markov chain eventually may go to 0. So, and then once it gets to 0, it's constrained to be 0 from then on. So that is one approach that we've been exploring here to understand. So we assume X is related to Y, and then we assume this underlying stochastic process that will transfer Z to 0 at some time in the past. And then we can get the probability mass function of this delay time. We can also have, I don't know if that's on the next slide. So the Markov chain may also have time-varying probabilities, transition probabilities. They don't have to be the same transition probability, especially over a long period like years for a particular disease. So depending on, so this is showing the different variants of the disease and how the different variants are in the wastewater over time. And there's mixing that happens there, but there are also clear signals that the variant is changing over time. And we know that alpha, beta, omicron, etc. So you also want for this model, for the Markov model, to be able to be flexible so that you have a time-varying transition probability that will depend on the period that you're in. So that's also something as a next step that we considered. And then finally, the last piece of this that we're considering right now is that there are well-defined periods where the transition probability might be fixed as we go from Omicron 1 to Omicron 2. But in between a transition period, you might have mixtures of transition probabilities. So as one variant leaves and the other variant comes into play, then there could be a mixture of those transition probabilities that will define whether or not one variant is more dominant than another as the other one becomes more dominant. So really interesting statistical models that could have a variety of applications besides the COVID or besides infectious disease, because this is just a relation between a variable and a response and how lags of that variable affect the response. So that's one example. And then, of course, we haven't got here with regards how to handle small communities or how to handle spatial aspects. We have data from across the globe, but we've been focusing only on Canadian sites, including sites at Waterloo and at Ottawa in particular. So big scope here for lots of verticals that will build into a horizontal understanding of how disease surveillance can be monitored effectively. And so I've given some of the challenges there. So this is where I need to skip if I want to give the students who are here an answer to did they or did they not get an award. So to shorten the talk, because we have apparently a lot of award winners, I'm going to jump through this one. Okay, I can tell you a little bit about it. It's an analysis that uses two building blocks. The first building block is something called joint models. So we want to there are two key aspects of a fire. Its size and how long it lasts. And these two are correlated. And so if you think about a bivariate model for each fire that says T1 is size, T2 is duration, then you might want to think about how to correlate those two responses. And we've done some work correlating them using joint models. And then the second piece of this is, so you've got a joint model for a particular fire, but we also saw that fires didn't come from the same population. It looked like they were coming from mixtures, so different populations. And there are two clear ones, and those are the ones that are attacked and are small fire suppressed immediately tend to be the short and small fires. And then there are a whole bunch of fires that have bad weather conditions. You know, it's really hot, the ground is dry, or maybe they escaped, or maybe they weren't even suppressed at all. And so those tend to be the long and big. Eventually we saw that there were 4 clusters in the data, not 2, but originally we thought that there would be these mixtures in the population. So a joint model for the 2 responses, and then layering on that a mixture model for each of these bivariate responses. So to jump, what I think I would love to do is to go here. So how did this work begin? So this is, again, a real disappointment for those of you who want to look at the analyses and the statistical models. But if you're really interested in this joint mixture model, the work is actually published already, and so happy to refer you to that. What happened here is that you know that there's a serious problem with regards fires. The Ministry of Forests reached out and asked, I think they must have asked Richard. I don't know who they asked, but they asked the departments of in both SFU and UBC and UVic, you know, who could help them with this. And I had relationships with the Ministry of Health The Minister of Health talked to the Minister of Forests and said, listen, there's this woman who knows about spatial analysis and statistics, and she knows how to talk to us. Why don't you talk to her? Then I started talking to John Braun about this, because he's really interested in forest fires. Then we got this big problem, which is, and I'll go backwards afterwards. They want to know how to estimate area burned. So bringing John in allowed me to bring in some brilliant fire scientists from the University of Toronto and some from the Pacific Forestry Center. And so, you know, can't work with students without money. So then applied for various project grants in order to support this. Some of you may know we started off with what was called the National Program of Complex Data Structures. Gave us such a good start, because from there we got a national network that evolved, and we also got provincial funding as well as federal government funding, major pieces of funding. Now we had something like 50 students across Canada who were going to solve this problem and give the ministry an answer. So this is sort of the starting point for me, starting with the fire scientists to say, tell me about this problem. How do I understand it? And then Francis Zwires, you know, Francis is a great climate scientist. He also sat down with me and said, okay, there are serious climate linkages here with fire occurrence. So we started to map out, you know, what's going to affect, so high level in the atmosphere, medium level in the atmosphere, wind speed, how all of this affects when snow melt happens, how much snow we have underground, the flammability of the fuel, where lightning strikes happen, fire spread days, and then how this affects the length of the fire season, the number of fires, person-caused fires as well, and all of these link into area burned. So it wasn't easy, by the way, trying to map all of this out in collaboration with our fire scientists. And then the next step was, well, what do we know well? Because the problem's too big. So remember, this is the horizontal, and in the statistics world now we need to delve into the verticals where we just don't have enough information, or we don't have models, or whatever. So the next step was going back in history and trying to understand, you know, what's well established already. And so getting a good grip on these pieces are well known, these pieces are not. We really need the statisticians, the computer scientists, to work with us to articulate how models flow, and then also to build this big model. That was, for me, a very exciting piece of knowledge creation, and that led then to dispersal of, you know, here are the priority projects we want for these. I don't remember how many scientists we had. Maybe John can comment on that, but it was across Canada, all the brilliant forest fire scientists. We even had the fire chiefs as part of the network. And so we would do a call for proposals to identify whether or not we can get better information on the specific aspects that we were weak on. And for some of these, we also had to do experiments using wind tunnels, and we got great access to wind tunnels in order to support that work. And then from there, trying to build a big model. And the final piece I'll say here is that, you know, when you work with the government and they give you a problem and they give you lots of money to solve the problem, and they say, we really want to get a grip on area burned and how that is going to trend, it just changes as well over time. So coming back to the problem, they then defined that what they wanted is risk analysis. They were more interested in risk analysis, so we had to go all the way back to the drawing board and try to understand what's the expected risk by looking at all the hazards and the intensities, and then also putting out new calls for proposals to identify the work in these areas. So The whole project evolved through a lot of great collaborations, and there are many students in this audience who participated in this work and who helped drive the analysis. And we've been able to build a model using computer scientists also to support these deliverables that were required. I'm going to talk now. So those folks want me to have now less than 10 minutes. So I'll say that there are so many challenges in working in these big teams. And some of you who've worked in it know them all. The people who are talking to each other, they talk to each other, but they're not really talking to each other because the words that they're using have different meanings in different disciplines. And as you get experience in this and you listen on, then it's easier to be able to interrupt a conversation and say, I don't think that we're communicating here. Here's what this person is trying to say. And then make sure that we've got the new members of the team well oriented. There's also challenges with regards intellectual property. So a student has a goal. They want to get the analysis done, so they get their thesis. So they get out of there, so they get a job. Whereas at the high level, they're deliverables. And the funding is often contingent on reporting on the deliverables. So there are always tensions between, I just want to answer this problem, I just want to get my thesis done, I want to leave, versus I want to weigh into this big analysis and problem. So those tensions never go away. The recognition is different in statistics, not so much in statistics and fire science, but if you are working in a discipline like SHRC, the kinds of recognition and metrics are so very different. It's difficult to understand how everybody's going to be on the same page with regards what are the outcomes here in terms of publications, etc. But there are also lots of benefits, and the benefits really relate to trying to work to solve some of the big problems that are facing Canada. And the fire science problem is a big one, and many of you work in genetics. I think Jerry's moved on to genetics now for quite some time. There are some really big problems in that field. I see Shelley is also here. So there are key areas where there are some serious problems, and I think I've got I'm going to come back to this because I'm not so sure what's happening. Oh, I think what's probably happening is that they want to get on with the students, but I can talk through this section. So I see in this conference there is a lot of discussion about data science. And data science is now becoming very interesting for us as statisticians. And it's not just statistics. It's typically somebody in some scientific field, computer scientists, a whole variety of individuals. So we can work it that way if that's easier. So I wanted to close with a few words about data science and what I see happening in this field. And that also links with artificial intelligence and the whole movement towards artificial intelligence right now and how statistics and data science weigh into that. I see that there are things called data lakes being created, and those of you who work in this area will know what I'm talking about. So this is a mechanism to be able to amass large quantities of data for these AI tools. So, for example, you might put in one data set on taxi rides by a particular company, And then you might identify that one of the taxi rides, yeah. It's working now? Okay, perfect. With this, you think?
Right.
Yeah. So all of these fields now being there. The idea about data lakes is that previously as a biostatistician, we'd go through each of the data pieces to identify, wow, this has got to be out of line. We need to clean this data piece. Now these data lakes don't do that. They don't talk to people. What they do is they look for other data that are close by. And this is an example of taxi rides that look like hundreds of dollars for a particular ride. Instead of going back to the data provider to check this, what they do now is they go into the system of data to see who else has traveled from A to B, about that time of year, about that time of day, and then use that to correct the data. And this is all done automatically by, artificial intelligence rules. So with these data lakes and data correction techniques, it's all now about matching and analysis and algorithms that do data cleaning and data correcting. Very, very different from what we do as statisticians, trying to go back to the data source to understand. So, and I go back to sending Cindy up north to understand the data. So much knowledge gained there. So data lakes are, I don't know if you have your eyes on this, but data lakes and the techniques that are used in data lakes to clean data, to find underlying bases whereby we can develop models in the AI world. It's a very different way of doing things than how we do it as statisticians. The other thing that data lakes are used is to answer questions for secondary analyses. And, fundamental to a statistician, a biostatistician, is what's the aim, what's the scope, and then use that data to analyze those particular aims. Now with data lakes, there isn't really an understanding of primary aim or secondary aim. It's simply just using assemblies of data in order to solve any question that you want to come up with that you think that the data might solve. And I've asked these questions of AI because we're working to develop tools for the federal government with regards how they use AI in their organizations, and plunking down a whole bunch of co-op students actually from the University of Waterloo to do this. And there isn't a sense that they understand that one agency might have collected data for one purpose but may not be able to be used by another agency without some careful thought about analysis. But this is just pervasive so it needs a little bit of watching. And now they're talking about model lakes. So instead of data lakes, putting models into big frameworks in order to do simulations, and using the various models tied together to form a big, massive simulation model for a particular problem. So that's also, this is a new technique that's being developed that's going beyond the data lake techniques. So I think I'll close here. One of the things that I'll close with is that, so these are the Government of Canada priorities. So they were defined last year, and they're priorities that will drive funding, what NSERC is going to fund, what various Environment Canada, Health Canada, etc. And it's on their website, and there's a lot of detail as to specifically what they're interested in that guides all the government agencies in their funding portfolios. So I've only put the top level there. So healthy Canadians, sustainable food systems, and then the whole EV sector, energy sector, the clean tech sector. And then on the other last piece is where we are. the technologically advanced Canada is where you'll see data science and statistics and AI. And that piece is for developing new tools in data science and statistics and AI. But you also find it at the bottom. So the way the Government of Canada has framed it is that we want to develop new tools, but they underpin everything that we do in all areas. So there is this fundamental block at the bottom, and I've used this slide for quantum, so you'll see quantum there, but data science is in there as well. So it underpins healthy Canadians, sustainable food systems, clean and rich Canada. And that, I think, has also been a tension for our society. Are you, where do you lie? Do you lie in the piece that's underpinning the growth of other areas? Or do you lie in the piece that's driving the fundamental new discoveries for the discipline itself? So there have always been tensions there in our society and in our discipline at granting councils, how they're assessed. And I can tell you the Government of Canada values both. So they value the technological developments, but they also see it as fundamental to the advancement. And why? Because we're a digital society. So critically important. So thank you so much, everyone, for listening to me. And I did my best to finish at 9:15 so that we can get the students out the door. And just to let you know, I was meant to finish at 9:20, 9:25. So I've done my job for you. Such a pleasure being here and such a thrill to be away from issues. And I hope that you enjoyed some pieces of my talk.
Thank you very much, Charmaine. So now the floor is open for questions or comments.
That, Charmaine, I can't resist the one comment as far as the federal strategies. There's one, I think, piece missing between enabling technologies and social science, ethics and stuff, and that's called feet on the ground. If you think of our healthcare system, you need to have integrated into this whole enterprise the people that are delivering health services. Forest fire management, you have to obviously integrate with the people that are fighting forest fires with all the different ways and means. I just wondered if you had a short comment on that. Because that seems to me that's one thing that the federal government is exceedingly poor at, is the execution phase.
Right, so that is a really good point. In the healthcare system, we see that terrifically, and especially post-COVID, and the challenges that are faced. And I showed you the slide where initially they wanted to understand area burned, and then we spent countless hours trying to figure out, backtrack all of that, and then it changed into something completely different. I'd say the political side is tough to work with because they are, there's a lot of push and pull there depending on what you, the people, see as most important at one time or another. And that connectivity to the underground is such an important piece. Jerry, I'm going to be sure to mention it next time. We know, John, I don't know if you want to speak to this, but we know that we were working with the fire scientists, and out of the blue, one day a fire chief wrote to us and say, why aren't we in there with you? And I think that we didn't even think about bringing in the fire chiefs, and now all of a sudden we were going to see each of the main fire stations and talking to the fire chiefs and giving presentations. John, I don't know if you wanted to add anything there, but it was an eye-opener for us that even though we thought we were so enlightened, we were completely out of it in terms of bringing in all the right people with the boots on the ground, as you say. Did you want to add anything?
There are a couple, can you hear me? There are a couple of things I can add. fully in agreement with your comment. And in fact, actually right now, there's a growing divide again between academics and the fire science community, or the fire management agencies. All these calls for proposals from the federal government for money, and a lot of people are because wildfire is such a hot topic. Sorry. There are a lot of academics who, great opportunity to get lots of money, and the fire management agencies are now saying, we don't actually need to fill our warehouses with things that we're never going to use, and we're not that interested in publications. We really need knowledge mobilization. And so this is a critical time. The other point is that the indigenous communities are very, they're part of this, and we need to make sure that whatever we're doing includes them.
Mm-hmm.
So other questions?
So just a question on big data, data collection, data sets, and AI, particularly in healthcare, and getting many groups together. There are many hands in the pot, and so many people can say no because there's a fear of, especially in healthcare data, sharing data for AI purposes. There's a fear that, say, an evil company is going to mop it up and make money off of it while the rest of us are trying to do research in more of an open source way. What's your argument as someone who's in your office overseeing and trying to get all the groups together in the various departments? What's your argument for the naysayers to say, well, we should be doing this research, and how do we mitigate some of the fears of what people might be worried about with companies getting a hold of AI and trying to make money off of it versus trying to do research?
Yes, so I have to say that I'm on the side of the naysayers, so we're in a little bit of a problem here. But what I will also say is that the federal granting agencies, NSERC, SSC, and CIHR, are so concerned about AI and the advancements of AI, and especially CIHR for the health arena, that they struck a task force to provide a policy on the use of AI in research. And that policy has specific elements related to AI for health research. The task force gave preliminary recommendations, and those recommendations are now being, there's a consultation process with the AI community, the health community, etc. And I expect that by the end of June, there will be a policy statement regarding the use of AI. And there are also policy statements in other countries. By the way, the US is ahead of us on this, and right now there's a lot of prohibition with regards AI for specific kinds of health research, but we will have our own, so I would probably not want to comment on that with my own viewpoint, given that I know that there is a policy, a government policy that will be coming out for Canada as a whole. And if you don't obey that policy, you're going to be in violation of what's called responsible conduct of research. So that is the same policy that, you know, if you make up health data and you use it for publication, that's the same framework. So they're viewing it very, very strongly. It should be out very soon.
So any other